Welcome to The Explainer. Today, we're tackling a topic that is just absolutely fascinating and, frankly, a little mind-bending. We're diving into the economics of AI recursive self-improvement. Now, you've probably heard that term tossed around in flashy headlines or late-night sci-fi debates, right? It's this wild idea of an AI getting smart enough to build an even smarter AI over and over again. But today, we're skipping the hype completely. Instead, we're going to build a rigorous mathematical engine to figure out exactly what it takes for an AI to actually accelerate its own development in the real world.
To really set the stage, think about this famous quote. Way back in 1965, mathematician I.J. Good wrote, "An ultra-intelligent machine could design even better machines. They would then unquestionably be an intelligence explosion." It's basically the ultimate sci-fi premise. But here's the thing, a lot of people treat this like it's just an inevitable magic trick. They assume that if we fully automate AI research, boom, we're guaranteed to get an intelligence explosion. But, as we're going to see today through some genuinely brilliant economic modeling by Tom Cunningham and his team at the Elasticity Institute, an explosion might not happen at all if you run into diminishing returns or everyday bottlenecks. So we're going to enthusiastically pivot right past the philosophy and unpack the actual economic science behind this concept.
All right, so here is our roadmap for today. First up, we'll define exactly what recursive self-improvement actually means. Second, we'll build out our baseline model. Third, we'll look at the real-world bottlenecks AI faces. Fourth, we'll contrast narrow versus broad capabilities. Fifth, we'll zoom out to look at the massive economic feedback loop. And finally, we're going to answer the million-dollar question. Are we accelerating right now?
Okay, starting with Section 1, defining recursive self-improvement. Let's move past the sci-fi. To do this properly, we really have to throw out all those vague, inconsistent definitions people use and get super precise. You know, people often say recursive self-improvement when they just mean a technology that helps improve itself. But honestly, by that logic, a hammer helps build a better hammer. That's not what we're talking about. What we're actually hunting for is a self-sustaining acceleration. That only happens when AI systems become good enough to accelerate their own capabilities without needing any extra outside help, like pumping in more human engineers or vastly more training compute. That right there is our North Star. We are looking for an engine that literally powers itself.
So how do we measure if our engine can actually power itself? Well, we use a specific economic tool called elasticity. Don't worry, it's actually pretty simple. Elasticity is just a measure of responsiveness. It's the percentage change in an output caused by a 1% change in an input. Think of it like this. If we put exactly 1% more fuel into our engine, how much extra speed do we actually get out? If we put in a 1% increase in AI capabilities, do we get a full 1% boost in new algorithmic discoveries? Or is it less? Or maybe more? Keep this concept tucked in the back of your mind, because elasticity is the fundamental math holding our entire engine together. Moving right along to Section 2, the baseline RSI model. It's time to build the engine.
We're going to build this engine step by step, and we're starting from the absolute basics of how innovation works. Our starting point is the classic Jones model of innovation from 1995, but we're applying it to AI. Picture this. At the very top, you've got R&D labor, the human researchers. They come up with algorithmic improvements, which then trickle down to increase our overall stock of algorithmic efficiency. But then, there's a crucial feedback loop that goes right back up. You see, our current level of algorithmic efficiency directly affects our ability to find brand new improvements. Historically, across industries like agriculture or making microchips, the elasticity of this loop is well below 1, which simply means the good ideas get harder to find over time. Progress just naturally fizzles out unless you constantly pump in more and more human effort.
Now, let's bring modern AI into the mix. We're adding capabilities and training compute to our mental map. This is our baseline model for recursive self-improvement. Algorithmic efficiency combines with massive training compute to generate actual AI capabilities. And then, and this is the absolute key, there's a feedback loop pointing from those new capabilities straight back up to algorithmic improvements. The AI itself is now helping to discover the new algorithms. For this whole crazy system to hit a self-sustaining acceleration, the combined elasticity of these loops has to be strictly greater than 1. The math demands that an increase in our current ideas has to generate an even bigger proportional increase in the discovery of new ideas. But as we all know, math doesn't operate in a vacuum.
Which brings us perfectly to Section 3, real-world AI bottlenecks, the friction in the system. Look, any engine, no matter how beautifully designed it is on a whiteboard, is going to run into friction. The scary reality is that the elasticity in our core feedback loop can easily drop over time because of everyday bottlenecks. What if the AI can only handle certain parts of the research, but it completely lacks human intuition, or that sort of subjective taste for a good idea? Suddenly, human labor becomes a massive bottleneck again. Or what about compute? We could have insanely smart AI capabilities, but if we don't have enough experimental compute to test their new algorithms, or enough inference compute to just run the agents, the whole loop grinds to a halt. And then, there's data. If we literally run out of high-quality human-written text to train the next generation of models, capabilities could just hit a brick wall. Any single one of these constraints acts like a giant speed bump, weakening our loop and killing that self-sustaining acceleration.
Let's shift over to Section 4, narrow versus broad capabilities. Think of these as different gears in our engine.
We really need to understand that AI capabilities aren't just one big, uniform blob. An AI might develop absolutely incredible, narrow capabilities. Like, it becomes an absolute genius at optimizing search algorithms, writing back-end code, and crushing AI research benchmarks. That would supercharge our core feedback loop. But that exact same AI might be totally useless at broad capabilities, the really messy, economically valuable real-world stuff, like managing a global supply chain, driving a truck, or negotiating a legal contract. So you could totally have a scenario where AI is rapidly evolving its own internal coding abilities, but it isn't fundamentally transforming the broader global economy yet. It would be a very, very jagged technological leap.
All right, Section 5, the economic feedback loop, pumping the fuel.
So what actually happens when those broad capabilities do start to take off? If we zoom out to the whole macroeconomic picture, as AI gets more capable across the board, it drives massively higher economic output. We're talking a massive boom in global GDP, or at least skyrocketing revenues for the AI labs. And what happens to all that new wealth? It gets relentlessly reinvested. That economic output flows right back into buying way more experimental compute, inference compute, bigger training runs, and gathering massive new data sets. This is a staggering secondary feedback loop. Even if the pure algorithmic AI-improving AI loop isn't quite enough to go infinite on its own, this tsunami of money and resources from the broader economy might be exactly what pushes the entire system over the edge into self-sustaining acceleration.
And finally, Section 6, are we accelerating now? Let's check the dashboard. All right, moment of truth. It's time to plug some real numbers into this engine we just built and see where humanity actually stands today. This is the big question this entire explainer has been leading up to. We've got the models, we know the bottlenecks, we understand the feedback loops. So, what happens when we calibrate everything with real-world data right this second?
Well, based on the research using data tied to the Epoch Capabilities Index, the mathematical threshold we need to hit is 15%. For our engine to finally cross that line into a self-sustaining acceleration, to run purely on its own momentum without needing more human help, a 1-unit increase in AI model capabilities must result in at least a 15% higher return in AI R&D productivity. 15% is the magic number. And here is the dramatic reality check. Based on a rough back-of-the-envelope calculation using reported data from recent AI coding agents, that return on productivity is currently sitting at just about 9%. So what does that actually mean for us? It means the engine isn't self-sustaining yet. The loop is absolutely happening. AI is, without a doubt, helping to build better AI right now. But the system is still fundamentally reliant on scaling up human effort and pouring in massive amounts of external capital.
But I want to leave you with this final, incredibly provocative thought from the researchers themselves. They noted, feedback loops are not currently strong enough to generate a self-sustaining acceleration, though they appear to be strengthening. Think about that. We might only be at 9% today, but that number is not standing still. The gears are turning faster, billions of dollars are pouring in, and the models are getting sharper every single month. The conditions aren't met today, but with these loops getting visibly stronger, we all have to ask ourselves what exactly happens to the global economy the very second that dial finally ticks past 15%. Thank you so much for joining me for this explainer. I hope it gave you a much sharper lens to look at the future of AI.